Have you ever walked past a freight train late at night and wondered why the locomotive was still running, even though it wasn't moving? It seems like an enormous waste of fuel. A modern freight locomotive can burn around 4 gallons of diesel every hour while sitting completely still. Across North America, that adds up to hundreds of millions of gallons every year. At first glance, the solution appears obvious. Shut the engine down and let the crew spend the night in a nearby hotel. After all, hotels are more comfortable, quieter, and surely cheaper than leaving a massive diesel engine idling for hours. Yet railroads often choose the exact opposite. The reason has very little to do with convenience and almost everything to do with engineering, regulations, and economics. Behind this seemingly simple decision lies a combination of massive diesel engines, air brake systems, limited onboard electrical power, strict federal work hour rules, and decades of operational experience. To understand why, we first need to look inside the locomotive itself. Unlike the engine in a car or a pickup truck, a freight locomotive is built for a continuous heavy-duty operation. Engines such as the GE Evolution Series and EMD 710 are enormous medium-speed diesel engines designed to pull trains weighing thousands of tons across hundreds of miles without interruption. Everything about these engines is optimized for reliability under constant load rather than frequent starts and stops. One of the biggest reasons railroads hesitate to shut them down is temperature. While the engine is running, lubricating oil circulates through every critical component. The oil remains warm, flows easily, and creates a protective film between moving metal surfaces. Coolant also stays at its proper operating temperature, preventing thermal stress throughout the engine. Once the engine is switched off, however, everything begins to cool. As the oil temperature drops, it becomes thicker and moves less freely. Imagine pouring warm honey compared to honey that's been sitting in a refrigerator. The colder it becomes, the harder it is to flow into narrow spaces. The same principle applies inside a locomotive engine. Critical parts such as piston rings, cylinder liners, crankshaft bearings, and turbocharger bearings all depend on immediate lubrication during startup. If the oil is too cold, it cannot reach these components quickly enough. For a few brief moments after startup, metal surfaces may contact each other with far less protection than intended. Those few seconds might not sound significant, but repeated hundreds or even thousands of times throughout an engine's life, the wear becomes substantial. Cylinder liners slowly develop scoring, piston rings wear faster, and internal clearances gradually increase. Over time, compression efficiency decreases, oil consumption rises, and expensive rebuilds become necessary sooner than expected. The turbocharger presents another challenge. Modern freight locomotives rely on large turbochargers that rotate at extremely high speeds. Their bearings float on an incredibly thin layer of pressurized engine oil. If that oil is cold and sluggish, lubrication during startup becomes less effective. Repeated cold starts can shorten the service life of these expensive components, leading to repairs that cost far more than the fuel saved by shutting the locomotive down overnight. From a maintenance perspective, the calculation is straightforward. Fuel burned while idling is predictable and relatively easy to budget. Replacing turbochargers, rebuilding engines, or repairing worn cylinder assemblies is far more expensive and takes locomotives out of service for extended periods. As a result, many railroads prefer to keep engines warm whenever practical. Only when auxiliary systems can safely maintain engine temperature does shutting the prime mover become an attractive option. But protecting the engine is only part of the story. A freight locomotive isn't simply an engine on wheels. It is also the heart of an entire air brake system that keeps thousands of tons of freight under control. Every freight train depends on compressed air to operate its brakes safely. An engine-driven air compressor continuously fills large air reservoirs and maintains brake pipe pressure throughout the train. Under normal freighted operations, that pressure remains around 90 pounds per square inch. As long as the compressor keeps running, the braking system remains fully charged and ready for service. When the locomotive is shut down, however, the compressor stops as well. Although the reservoirs don't empty immediately, compressed air slowly leaks through valves, hoses, seals, and numerous small connections found across an entire train. Hour after hour, pressure gradually falls. Eventually, before the train can move again, the locomotive must restart and rebuild the entire air system back to operating pressure. Depending on weather conditions, train length, and how long the locomotive has been shut down, this process can take several minutes or even considerably longer. Until sufficient pressure has been restored, the train cannot safely depart. For railroads operating on tightly scheduled main lines, even relatively small delays can ripple across the network. A train waiting to recharge its brake system may miss its assigned departure slot. That delay can force dispatchers to reschedule other trains, creating congestion that spreads far beyond a single location. What appears to be only a few extra minutes beside one locomotive can eventually affect dozens of trains moving across hundreds of miles. Naturally, this raises another question. If keeping crews comfortable overnight is so important, why weren't freight locomotives designed with dedicated hotel-style power systems from the beginning? The answer comes down to priorities. Passenger locomotives and freighted locomotives may look similar from the outside, but they were designed for completely different jobs. A passenger locomotive often supplies electricity not only for itself, but also for an entire train full of travelers. Heating, air conditioning, lighting, kitchens, charging outlets, and onboard electronics all require a continuous source of power. That's why many passenger locomotives are equipped with dedicated head-end power systems capable of delivering hundreds of kilowatts. Freight locomotives were never expected to perform that role. Their primary mission is simple: move as much weight as possible over long distances with maximum reliability. Because of that, nearly every design decision favors pulling power, fuel capacity, and durability instead of crew comfort. The batteries installed on a typical freight locomotive are intended for one primary purpose: starting the main diesel engine and supplying essential control systems. They were never designed to operate climate control systems throughout an entire night. If crews attempted to rely solely on battery power for heating or air conditioning, those batteries could easily be depleted before morning, leaving the locomotive unable to restart without outside assistance. Adding larger battery banks sounds like an easy solution, but every improvement comes with compromises. Larger batteries increase weight, require additional charging equipment, occupy valuable space, and eventually need replacement. More electrical equipment also introduces additional wiring, sensors, and electronic components that require inspection and maintenance throughout the locomotive's service life. For railroads operating thousands of locomotives, even small increases in maintenance quickly become significant expenses. For decades, engineers concluded that simplicity was often the better option. Instead of installing large hotel power systems that crews might only use occasionally, railroads accepted that the main engine would continue idling whenever necessary. As fuel prices increased and environmental regulations became stricter, however, that approach became harder to justify. Railroads began looking for alternatives. One of the first successful ideas was the auxiliary power unit, commonly known as an APU. Rather than keeping the enormous prime mover running all night, an APU uses a much smaller diesel engine to provide heat, electrical power, and enough energy to keep the locomotive ready for service. Because these engines are much smaller, fuel consumption drops dramatically. Instead of burning several gallons of diesel every hour, an APU may consume only a fraction of that amount while maintaining acceptable cab temperatures and preventing the main engine from becoming excessively cold. On paper, the concept seemed almost perfect. In practice, the situation proved more complicated. An APU is still another engine that must be maintained. It requires filters, fluids, inspections, sensors, software updates, and periodic repairs. Every additional system installed on a locomotive creates new opportunities for failures that would never have existed before. Some railroads discovered that integrating APUs into existing fleets required far more maintenance than originally expected. Components exposed to constant vibration experienced accelerated wear. Electrical connectors developed corrosion, and diagnostic software sometimes required recalibration after routine servicing. While each individual issue might seem minor, together they increased the amount of time locomotives spent in maintenance shops. Automatic start-stop systems represented another attempt to reduce unnecessary idling. These systems continuously monitor engine temperature, battery voltage, coolant temperature, and outside weather conditions. If everything remains within safe operating limits, the locomotive automatically shuts itself down. When temperatures fall too low or battery voltage begins dropping, the engine restarts without any action from the crew. This approach has helped many railroads reduce fuel consumption while limiting unnecessary engine wear. But even these systems have limitations. A weak battery, a faulty sensor, or an unexpected software problem can prevent an automatic restart. During extremely cold winters, temperatures can fall faster than expected, leaving crews with uncomfortable working conditions or forcing operators to manually override the system and keep the locomotive running. Battery-powered switching locomotives have also demonstrated what the future could look like. Instead of relying entirely on diesel engines, these locomotives use large battery packs for lighter duties around rail yards. They produce significantly fewer emissions and consume much less fuel. However, battery technology remains expensive. Charging infrastructure is limited, and today's batteries still struggle to match the range and continuous power required for heavy mainline freight service. For that reason, battery locomotives currently occupy only a small part of the industry. Technology has unquestionably improved over the past 2 decades. Modern locomotives are far more efficient than those built a generation ago, and idle reduction systems continue to become more reliable every year. Even so, technology alone doesn't determine whether crews spend the night inside a locomotive or in a hotel. Another factor often has an even greater influence, and that factor isn't mechanical at all. It's the law. While engineering explains why locomotives often remain running, federal regulations explain why crews don't simply head to the nearest hotel. In the United States, freight train crews are governed by strict hours of service regulations. These rules limit how long engineers and conductors may remain on duty before they are legally required to take a mandatory rest period. Once that limit is reached, the train cannot continue until a properly rested crew is available. Unlike many other professions, there is very little flexibility. If a crew reaches its legal working limit while hundreds of miles from a major terminal, the railroad must immediately find the safest and most practical solution. In many cases, that solution is to let the crew rest where the locomotive is already located. Moving them to a hotel is not always as simple as it sounds. A transportation vehicle must first reach the train's location, which may be along a remote section of track far from the nearest town. After the crew reaches a hotel, the same process must be repeated when their rest period ends. Meanwhile, replacement crews, dispatchers, and train schedules all have to be coordinated around those movements. Every additional step introduces another opportunity for delays. And on a busy railroad, delays become surprisingly expensive. At first glance, leaving a locomotive idling overnight appears wasteful because of the fuel consumed. However, railroads don't compare fuel costs alone. They compare the total cost of every available option. Consider a typical overnight stop. Keeping the locomotive idling may consume well over $100 worth of diesel fuel during a full rest period. Sending a 2-person crew to a hotel requires transportation, hotel rooms, additional crew logistics, payroll costs, and administrative coordination. Those expenses can quickly exceed the value of the fuel that would have been burned. But the largest cost isn't always visible. Freight railroads operate according to carefully planned traffic flows. A train that misses its assigned departure window may be forced to wait for another opening among dozens of other trains sharing the same route. That single delay can spread throughout the network, affecting freight deliveries, connecting trains, yard operations, and customer schedules hundreds of miles away. By comparison, burning extra fuel sometimes becomes the less expensive decision. For many decades, this economic calculation strongly favored leaving locomotives running whenever practical. Eventually, however, another factor began changing the equation. Public concern over emissions continued to grow. Communities located near rail yards became increasingly concerned about diesel exhaust and engine noise during the night. At the same time, fuel prices became more volatile, making long periods of idling far more expensive than they had been in previous decades. Environmental agencies also introduced stricter emission standards, encouraging railroads to reduce unnecessary engine operation whenever possible. As a result, idle reduction became a major industry priority. Railroads expanded the use of auxiliary power units, improved automatic engine start-stop technology, and introduced smarter locomotive management software capable of monitoring temperatures, battery condition, and weather before deciding whether an engine could safely shut down. Some companies also redesigned crew scheduling to reduce the number of overnight layovers in remote locations. Others invested in hybrid locomotives capable of performing switching duties using battery power rather than diesel engines. Each solution addressed part of the problem. None eliminated it completely. Cold weather still challenges batteries. Additional equipment still requires additional maintenance. Older locomotives built decades ago remain in service because freight locomotives are designed to last 30 or even 40 years with periodic rebuilding. Replacing an entire fleet simply isn't economically realistic. That means today's railroads often operate a mixture of older locomotives, modern diesel units, locomotives equipped with APUs, and newer idle reduction technologies, all working together across the same network. For train crews, reliability continues to outweigh luxury. After spending up to 12 hours operating a freight train, knowing that the locomotive will remain warm, ready to restart, and prepared for the next assignment provides confidence that no unexpected mechanical issue will interrupt the next shift. Until newer technologies prove they can deliver that same level of dependability under every weather condition, many railroads will continue relying on practices that have worked for decades. So why do train crews sometimes sleep inside the locomotive instead of staying in a hotel? The answer isn't laziness, outdated habits, or a lack of concern for comfort. It's the result of engineering limitations, federal regulations, operational logistics, and a careful balance between fuel costs, maintenance expenses, and network efficiency. From the outside, an idling locomotive may seem like an unnecessary waste of diesel. Inside the railroad industry, it's often the most practical solution available. As cleaner technologies continue to mature, that balance will gradually shift. But for now, the sight of a freight locomotive quietly idling through the night is a reminder that keeping a railroad moving isn't just about pulling trains. It's about making thousands of small decisions where reliability, safety, and economics all meet on the same set of tracks.